Okay, so last time we started with polynomial spaces in 2D, and yeah, we discussed how to construct these spaces, and also when we have a domain, something like this. So let me activate my pen. Yeah, when we have a domain like this, it could be complicated domain. What we did, we triangulated. It say that we divided by simplexes. So simplexes in this case is called triangulars, edges, and points. So all these elements are simplexes. So we divided by a finite number of elements. Elements in this particular case, they are triangulars. Then we have to keep track of these elements. So what we did, we numerated these triangles by k. So ki, it means here triangle of I, if triangle. And we say that the total number of triangles in this picture that we draw, like we, in general, we call it M. Then every triangular has three corners, and these three vertices, they have a coordinate, and they also have a global number. So this n is a numbering. You just put a lot of coordinates and you put some numbering. And we say that the total number of vertices in this triangulation will be denoted by n. So in this particular case. So we have n plus 1 vertices and m plus 1 elements or triangulars. Okay, then we define some mesh size. So we say that there's no unique way of defining mesh sizes in 2D. And one of the possible ways, we could just take a outer diagonal of the outer circle for this triangle or something like that. So we discussed and we say that we can use these Lagrange elements. So it is exactly the same description that we defined in 1D. And Lagrange basis functions, they are linear functions that are one at given vertex. For example, if you take this triangular, we put 1 here and 0 otherwise. So it's going to be like a tetrahedron with the height 1 located in given vertex. And for this triangular, we have 3 vertices. Therefore, we construct 3 Lagrange basis functions. And one can show that these 3 basis functions span the space of all linear functions inside this triangular. And since we have 3 independent basis functions, of course, we can also show that these basis functions are linearly independent. Then we say that the dimension of this linear space is 3 in this case. So our aim was to construct something for our domain, big domain. So we did triangulation, and we get the idea from the 1D approximation. And we say that for every node, we construct a head function or basis function, phi I, for example. So there was a misprint here. So this should be node xi, of course. For node axi, we define one basis function, which is 1 at this given node, 0 otherwise. So you see, like, if you take a restriction of this basis function in one triangular here, so if you just take a restriction in this little triangular, it's going to be the usual Lagrange basis function, which is defined there. So if you take a restriction with another triangular, for example, the neighboring one like this, so it's going to be another basis function. Of course, this is the usual Lagrange basis function inside the triangular. And so on. We say that for every node, we construct this kind of basis functions. These are tent functions, sometimes called. And one can show that a linear combination of all these basis functions defined on the nodal points construct our space. These are the spaces of continuous functions first, and they are piecewise linear. So we could also write that V is a continuous functions inside omega, and the restriction of V with Ki, this the triangular Ki, is a polynomial of degree 1 on Ki. And this is for all Ki's from this triangulation, something like this we can write. Okay, so we can of course define interpolation and projections, and this is something that we want to discuss today. So today we will talk about interpolation plus projection. And we will see that the definition does not change in, we are moving to one dimension higher, but interpolation and projection, they have the same property as we had in 1D. Then hopefully we will start with finite element in 2D. And yeah, of course, this part we touched a little bit in Scientific Computing 3 course, but today, hopefully, we will quickly go through. We will not go into small details, but the aim would be we want to prove a priori and a posteriori estimates. Okay, so this is going to be planned for today, hopefully. So we will see how far we go, otherwise we can continue next time. Okay, so what was the definition of interpolation? So what we did in 1D case. So let's say that we are giving this function f of x1 and x2. So it's like a surface in 2 dimensions. And we say that this function pf, we can of course put h little here. I will see if I have h. So in my notation, I put 1, so it is the same. ph of x, so I put x bar. I mean, it's the same as, x bar. I should say that x bar, it's a coordinates like x1, x2. So we are in 2D, we have two space coordinates. So we say that pi hf is interpolant of f if pi h of f is equal to f at every nodal point. So it equals to f xi at every nodal point. For every I equals to 0 all the way to n. So remember, we had n nodal points. I used the same definition of the mesh that we defined last time. So I just showed you a little bit quickly. So for every nodal points, the function, the value of the interpolant is equal to the value of the function f. And in addition, we say that this interpolant f lives in our finite element space. So they are continuous, and piecewise linear. So now you can think about a surface in 2D, like you draw some surface. Now you have to put several mesh points, and these mesh points are finite because the dimension of this VH is finite. And what you need to do for every mesh point, you just find a point on the surface of this function, and you assign it to your interpolant. So if you draw it in 2D, I have a picture in my lecture now. I can try to draw it here again. So we have some kind of continuous function like this. So this is f of x. And somewhere here we have this triangular. So this is our k, ki, for example. Then we have these nodal points. And for every nodal points, we assign. So we assign here 1 point here, second point, third point, something like this. And the function could be like curve in between because these are not linear functions. That's why fx does not necessarily live in our finite element space. But we construct a surface which passes through these 3 points. So this is going to be like this surface. I need to try to straight like this. So this is going to be this little surface here. This is going to be interpolant of f. And yeah, this was for this triangular. If you go to the neighboring triangular, you have to think that we glue this edge. So there's no discontinuity. These functions should be continuous. The neighboring should be like another surface which aligns with this function of x at given points. So at the vertices of the surface. So yeah, analogous description or picture in 1D. I can just remind you what was the interpolant. So we have some interval. We split it by a finite number of small intervals. This function f could be some smooth, but really oscillative function. It doesn't have to be super smooth. It should be continuous or discontinuous. It doesn't matter. Function f could be some arbitrary function. Then the interpolant is a function which exactly equal to this given function at these given nodal points. So something like this. And if we draw the interpolant here, it's going to be like this function. So this pi h of f works. So analogous in 1D. All right. Then when we have interpolation, the error estimate that we proved for 1D case also applies here. I just want to remind you without proving. So we have the following estimate: f minus pi hf in the L2 on this triangular k is less or equal to chk. So k, h is a diameter as we defined before, square, and this operator d2f, it's a mixed derivative of f. So I'm going to write it in a minute. So this is L2 on k. And we have, of course, several interpolation estimate. The second one could be the derivative of f minus phf L2k is chk. So we don't have any power here. Once you have a derivative, they cancel out with one power. And this is d2f L2h. So as I said, this capital D is a mixed derivative. So I have a, for example, for 1D case, it's df is equal to df dx1 square plus df dx2 square. It's a square root. Okay, so it's kind of a mixed derivative because f depends on x1 and x2. This notation, I think you're familiar with this. It's a partial derivative with respect to x, partial derivative with respect to y. And if you look, if you have 1D, so this term is gone, and this is going just to be a usual derivative. And yeah, so this is going to be f double prime, and we had it before. And this notation, the second one, is partial derivative of the second derivative is like df d square f dx1 square. We have a mixed term d2 dx1 dx2 plus df dx2 square. Everything is squared. Okay, so these are some of the standard interpolation estimates, and of course there are many similar estimates, and I think we will mostly use these two estimates when we do a priori and a posteriori estimation for the error in 2D. All right, so there is one thing that I have to mention. This L2, it's an integral, so I can just quickly say that the norm W square L2 K, it's an integral of W square dx on K. So, and we see that this function f in this situation, it could be any smooth function. So it could be, it has many derivatives. The second function is just a linear function. And we know that if you do numerical integration here to compute this integral, if W is just a linear function, we can introduce some numerical integration that the integral is exact. So I think this claim goes back to some of the scientific computing course, maybe 1 or 2, when you learned numerical integration, the integral of some polynomial, of course, this could be also a polynomial. Linear function is polynomial degree of 1. You can come up to some numerical integration such that the integration is exact. So in practice, whenever, in practice in finite element, all the matrices, they're integrals. So we have to calculate integrals. The elements are integrals. The right-hand side is integral. Now the error here is also integral. This L2 norm is integral. So in practice, there will be a lot of integrals we have to compute. And of course, it's not feasible to do exact integration for every given function that we come up. So it's going to be too much. We will have too many functions. And usually we don't know the nature of the functions in advance. Let's say that we have a differential equation, we have some right-hand side. We don't know what kind of type of right-hand side is that. If it is a polynomial, of course, we can come up to some numerical integration which is exact. But in general, it could be any function. So in practice, when we write a code like big libraries, the integral in finite element approximation, they are approximated is some kind of integration rule. So I'm just going to write the general formula for this, but I will let you read the note and book, because anyways, in the second part of the project, you will have to implement one of the integration rules. So instead of calculating the integral exactly, so this is 2D integral, we're going to change it by some numerical integration in some, these are quadrature rules. So in my notation now, W, Y, I, and here some weight, I will call the weight W bar, W tilde I. So here, this Y, I, they are quadrature points. And this W tilde is quadrature weight. So okay, so it says that, like in 1D, for example, if you want to calculate some integral here, so we can use a trapezoidal rule. The trapezoidal rule says that instead of calculating this integral, maybe I can just call it g of x, we can calculate the area which is covered by these trapeze. So we can calculate this area, and this is like one of the way of approximation. Of course, the exact integral is the area covered by this smooth function, but we change it to trapezoidal rule. It's like the area of this trapeze. It's exactly similar with this way. Now think about 2D. You have a mesh, and this triangle could be in any case, any shape, and you are going to put several quadrature points. So here, this is called quadrature point, the endpoints. You can put several quadrature points inside the triangle and calculate your numerical integration. Okay, so yeah, there are several ways of writing or calculating the numerical integration. For example, I can probably give one of the ways. In my notes, it's a second way, the vertex. The vertex-based quadrature points. So it says that if this one is our triangular, so we denote these nodes by n1, n2, and 3, and this is our triangular k. If you want to calculate integral on k, some function, so it's 2D function dx. The x is approximately equal to 1/3 g of n1 plus g of n2 plus g of n3 times the volume of k. So here, this notation is volume, or in this case, area. So area of k. So yeah, this one is one way of calculating the integral numerically. And of course, you see that this function g, it could be any function. You don't need to calculate integral by hand. And of course, in 1D, you could calculate definite integral by hand. You put the limits, it's easy. But in 2D, when the triangles, they have different complicated shapes, calculating integral in 2D by hand, and even if it is definite integral, it's not so easy. But numerically, we can approximate it in this form. So I think one of these integration rules are going to be used in the second project. So we can also extend the idea of L2 projection. If this object is interpolant of X, so interpolant, we can define projection P. So capital PH of X is L2 projection. Okay, so one of the, because the idea was we have this function space, this was VH, and we use some differentiable function F, which is not one of the elements of this space. So if F is not one element of this space, of course, it's some kind of vector which doesn't lie in the space. So this is our F of X. So the same discussion that we had for 1D case, we are going to find some element in that space, so we call it PHF. So PHF belongs to this VH, such that the error, this error, PHF minus F is orthogonal to the find such that the error is orthogonal to the finite element space. So this is like a projection idea that we did in 1D. We can use the same idea and give the following variational problem. Find PHF from the space VH such that the integral error, so this is PHF minus F, is orthogonal to this finite element space. That means that it's orthogonal to any elements from that space. The x is equal to 0 for all V from this space VH. So it's a projection problem. I think you did it in 1D when you calculated projection of your residual to the finite element space. In 2D, so the integration will be inside this domain, and we have to split the integration on the top of all these triangulars. So yeah, as we do it in finite element formulation, since this object from the finite element space, then there exists a sequence of coefficients. I call it psi j's. J is from 0 to n. N is number of nodes, number of vertices we have it in this triangulation, such that PHF is written as a linear combination of j equal to 0 to n, psi j, phi j of x. So these are the head functions that we defined yesterday. For example, this head function in this patch, it's defined in this form, 1 on this point I, 0 otherwise. So it's like it is defined in the whole domain in one small patch. It is not 0, but otherwise it's just a 0 function. Right. So we put this to the weak formulation here, and we notice that f is a given function. We just move it to the right hand side, and we construct. And also, since this formulation is true for any v from the finite element space, we can of course choose v to be phi I, one of the basis functions, and we get the following linear system of equations. So we are looking for psi's j is from 0 to n, such that this integral equation, so phi j x, phi I x, so this is x bar dx, is equal to f phi I dx. So this for all I equal to 0 to n. And of course, this resulting system is, we call it A. Let me just denote it by M. So M, we usually use A for the stiffness matrix, but this M is a mass matrix. So equals to the right hand side is vector B. And we obtain this system of equations, n plus 1 times n plus 1 system of linear equations. Okay, so once we find these coefficients, it's going to be our projection of the given function. And remember, when you find the projection, it finds the best approximation of this wavy function in the finite element space. So it doesn't have too much with the interpolation. So it's actually much better than interpolation. So there is one little exercise that I leave it to you. We proved for 1D case. So the exercise says, prove that PHF is the best approximation of function f of x in the finite element space. VH. So in other words, F minus PHF in the L2. So I don't write the subscript. If it is the L2 norm, is less or equal to F minus V for any V from this finite element space. Okay, so the idea of the proof, I mean, we did it in 1D, but the integral is going to be like integration in 2D. Then it's just you add and subtract the test function. So you open this, base it on the definition, then you add and subtract the test function. Then you split the integrals of the sum to the sum of the integrals. And you use Gagliarkin orthogonality. Orthogonality means that the error is orthogonal. This error is orthogonal to the finite element space. Then you end up to this formulation. So I just leave it to you as an exercise. Okay, but there is one thing that I can also mention. By using this property, we can actually say that F minus PHF can be less or equal to F. So instead of V, we can choose V to be interpolant of F, right? Because this is true for any V. The interpolant of V is also one of the elements on this function space. So minus PHF. This is also true. But for the interpolant, we have the following standard interpolation estimate. So F minus PHF is less or equal to some CH square, the second partial derivative that we defined a bit earlier of F in the L2 norm. So this actually shows that if F is twice differentiable, so it's smooth enough, then interpolation in this form is going to be like second order in the L2 norm. So this is the L2 norm.
Murtaza?
Yes?
So isn't that the interpolation error estimate, right?
Yeah.
So so it's a pi, right? So it's F minus pi H F.
Yeah, this one I
replaced. Okay, because you did the derivation directly. Okay.
Yeah, I can
okay.
I
guess I was like, where is that coming from?
Okay. No, I use the interpolation estimate. So since the left-hand side is less than that, of course, the left-hand side of this first estimate is also less than this estimate that we had.
Okay, thanks for the clarification. Yeah, I was.
Yeah. Sounds good. And we're gonna move forward now. And I think now we define what is interpolant, we define what is projection. And I think in one of the lectures, I say that this projection operator, so this derivation is closely related to Gagliarkin finite element approximation. So this is closely related, but I promised you that I will come back to this property a bit later, but that maybe now, maybe not now, but after a few minutes, we have to introduce an equation. Then we come back and we will see that actually this L2 projection, it's something that is reasonable. So this is like Gagliarkin formulation. It actually use this L2 projection. So let's move forward. So what was the idea here? We talked about the interpolation projection, and now we move to finite element in 2D. So we do the usual scheme. So we start with differential equation. we write weak formulation, we write finite element formulation. So I usually call it GFAM. Then we end up to linear system. Yeah, so sometimes we do a priori estimate actually after solving this, after coming to this part, before going to the linear system. Here we do a priori estimate. So there is something here. Before going to the linear system, before solving for finite element approximation, we can say that if you solve finite element, if you solve this differential equation with finite element, the error that you get is going to be that much. So that is called a priori estimate. And we do also a posteriori estimate, but that is actually after solving. So we come to the linear system, we solve it, we get this coefficient, we construct our approximation. So here we construct our UH. So it's an approximation that we get in finite element. And here we do a posteriori estimate. So now you see that the name comes actually from this scheme. A priori, it's before, so here we are solving. So this one is solve the linear system.
Murtaza?
Yes.
Yeah. So if I recall correctly, when you derive the a priori estimate, like you need to know somehow the original function, right? Because it was like the norm of f minus something. So you really cannot tell how big it is. Well, you can tell it's smaller than any of the other functions in the space, or something like that, if I recall correctly. But you really cannot tell, like, you have no indication, right?
Indication of what?
Of how big the error is going to be.
You have an indication of the error, provided that you have the solution. So here you know you asked a valid question. Here you know U is known.
Oh, okay. Yeah.
U is known, but you don't know UH because you didn't solve it for UH yet. So, I mean, provided that you know you want to say something about the UH. How good is this UH? I mean, without solving, before solving. But in this part, you don't know U, so U is unknown. But UH is known. Yeah.
Okay, so I mean, I guess you normally use the posteriori estimate because I mean, when you go into industrial applications, I don't know if
Yes.
how safe it is to assume that you never know U exactly.
Exactly. So, for example, for the Navier-Stokes equation, we never know that if U exists. I mean, that's a millennium problem. But we can calculate UH. I mean, we can calculate UH without knowing if U exists, pointwise. We can estimate the error. I mean, at least for some functional, maybe not pointwise error, probably it's not possible. But based on some kind of functional, we can do this approximation and estimation. This is called a posteriori estimate.
Okay, thank you.
Yeah, but here we don't know. UH is not known yet. Yeah, so these are schematically, I think, we sorted out that here, I can just draw some kind of line here, like this. Before this yellow line, we don't know this AUH, but assume that if you have U, not always, of course, we can do a priori estimate, and this a priori estimate actually is really hard for nonlinear problems. not for every nonlinear problem we can get a priori estimate, so it's super hard. But here, yeah, this is like before. A priori means before solving for UH. A posteriori means after solving for UH. We want to estimate how this UH, accurately approximates this U if it is known. All right, so we start with the same idea. We start with some differential equation, we define it. And the model problem that we consider here, it's a 2D Poisson equation. So of course, there is x depends x1, x2, it has two coordinates. And for simplicity, we assume that u is 0 on omega. So the boundary of this omega. And omega could be like this domain. It doesn't have to be unit square. It could be some complicated domain. And the boundary of this domain, we denote it by d omega. All right, so there are some definitions of what does it mean this delta. I mean, I'm sure that I usually do it in scientific computing 3 course, but let me just remind myself. So we use usually this notation is gradient, and gradient is a vector. So it is defined as d dx1, d dx2 transpose. So it's a vector. Then this Laplacian operator, this delta, is actually divergence of the gradient. So I will also define what is divergence. And divergence is the sum of these gradients something like this. So the divergence of that is going to be d2 dx1 square plus d2 dx2 square. So I'm not sure if I wrote this one correctly. So this operator is actually a scalar product of these two. So let me just denote this one as yellow. We have to double check if it's correct. So I move it somewhere here. So I just want to say that this operator is d dx1 d dx2 transpose times d dx1 d dx2. It's a scalar product. And this little delta is called Laplacian. Laplacian operator. Okay. So yeah. In my note, actually, I have it. There is A here. So 5. Oh, there's no A, but I give green. Okay. All right. So we often use integration by parts in 2D, and the analogous of integration by parts in 2D, it's defined by Green's identity or Green's formula. So it is written that integral, where is Green's? Integral divergence of some coefficient, in general, gradient of u v dx with the minus term is equal to integral ax grad u dot grad v dx on omega minus ax du dn v ds. So it is d omega. So we have to define some of this. Of course, there is du dn. It's a normal derivative to the boundary. So on the boundary, we define n. That's the outward pointed normal to the boundary, something like this. And the normal derivative here is defined normal vector times du dx. So it's a du dx1, du dx2. So there's no, and it's, yeah, we take a scalar product of that. Or it's normal, it has the two components, of course. Normal is n1 and 2. It's a vector. So it's normal times gradient of u. Yeah? So it's some kind of notations that we often use. All right, so this is analogous of integration by parts. And if I just remind you what was in 1D, so we can write in 1D minus a x u prime dx, here v dx from a to b is equal to a x u prime v prime dx, a to b, minus a u prime x v prime x. This is the boundary term. So this was integration by parts in 1D. Okay, so it was already 2 o'clock. I didn't pay attention to the time. So yeah, I just gave basic tools that we are going to use. So the next step after the break that we do, we come back to this scheme and we have to write a weak formulation, variational formulation. And at least we should be able to do a priori estimate today. So do you have any question now before taking a break? So if not, let's take a break and we come back in 10 minutes to 15. All right. So yeah, before the break, what we said, we discussed about this scheme, and we say that now we define with differential equation. We reminded ourselves some of the notation that we often use in 2D. There's a normal, there's a normal derivative to the boundary. We use gradient. Gradient is a function. Then there's a divergence. Divergence is a scalar. Divergence is acting to the gradient and becomes a scalar. So this is a scalar. And this is little delta. It's a Laplacian term. And we also recalled what is integration by parts in 2D. And usually they call it Green's formula. So it's here we have second order derivative on the left. We do integration by parts. We move this divergence to V. And this little dot, it's a scalar product because this one is a vector, that one is a vector, and this little dot is a scalar product. So I have to just to remind you, it's a scalar product. Okay, then we have this integral inside the domain, and we have these boundary terms together with the normal derivative to the boundary. So next step, we have to define polynomial space that we want to use. And for that, what kind of polynomial space we want to use, we have to write the weak formulation. We take the differential equation, in this case was minus Laplacian u. We multiply by some test function. We don't know to which space this test function belongs yet. So, and we integrate it. Fv dx in some omega. And after using Green's theorem, we see that the first part becomes gradient u times gradient v dx omega minus, there's a boundary term, the nu v ds in d omega, and equal to 0, equal to integral f v t dx, of course. This is in omega. Okay, and remember we have 0 boundary condition, and as we do it in for the 1D case, we choose the test function to be 0 on the boundary, so that the whole boundary terms, they cancel out. And by looking what kind of space we need for u and v, we can quickly see that we have a integral of the gradient of u, and we have an integral of v, and that's a space that we are looking for. And our variational formulation of weak form takes the following forms. Find u from this space capital V such that this space, we define it as all L2 integrable functions and all L2 integrable function of the gradient. And in addition, it is equal to 0 on the omega, such that the weak formulation, the following weak formulation holds. So grad u, grad v dx equals to fv dx and omega. This is true for all v from the space capital V. Okay, so yeah, usually we call it weak formulation. Remember, we talked about the strong formulation. The differential equation is usually given in the strong form because we call it strong form. The solution u should be twice differentiable in the classical sense. So in this case, this u should be from C2 in omega. It's twice differentiable. But we are looking for the solution in some wider space, and this, of course, this space capital V. It doesn't have to be differentiable per se at some certain points, because remember, when we use piecewise linear functions, the function does not have derivative at some points. But the important fact is that the points that that function is not differentiable. If you collect all these possible points inside this domain W, now omega, then the measure of this point is 0. So these are like countable points that differentiability is lost. So, but instead we require that the function should be square integrable and the derivative in this form should be square integrable. So there is an integral, of course, and if you have a discontinuity on the function on this on the integral, now on the derivative, then you write the integral on the domain by the sum of the small integrals, where you can calculate the derivative. So I think that could also work here. So that's why we call this solution U. You see, it doesn't have to be twice differentiable. We call it a weak solution. And sometimes we also call this formulation variational formulation, because U is fixed. We are looking for U here, but we are changing V So we are varying V. V is varying in this space. So that's why the name variational formulation comes from the fact that we are changing V. So for every V in the space, we can just write this formulation. So the next step is we have to calculate, of course, finite dimensional. We have to construct finite dimensional subspace of capital V. Of course, this notation is subspace. So subspace. So that the dimension of this VH is finite. Okay, just to distinguish that we have this zero boundary condition. Maybe it is nice to call this space V little zero. So we are looking for VH0, V0, and the dimension of VH0 is finite. So I will not repeat how to construct this VH0 because we did it in previous lecture, and I just quickly went through. We have to triangulate the domain, and for each element on the domain, we construct a space of polynomial functions, and we glue everything. We make sure that it is continuous. So provided that you didn't forget how to do this triangulation, like we did last time, I showed shortly in the beginning of this course, of this lecture, then the space that we are considering is the following. So these are all V's that V are continuous on omega, and the restriction of V with elements K, let me just write K, is the polynomial of degree 1 for simplicity. It could be also of degree higher for all K from the triangulation. So triangulation. So this belongs to the triangulation. And in addition, V equal to 0 on d omega. So this is finite element space. It's finite element because the elements, this case, they are finite. When we triangulate it, we divide it by finite number of elements. And inside each triangle, we have a linear function. And we say that in 2D, we just need to have 3 basis functions to define a linear function inside this element K. So in total, the dimension of this space is n plus 1. Remember that we put n number of points. So we say that if triangulation consists of n vertices, not n, but n plus 1, because we start the numeration from 0. So if we start from 0 to n, it's going to be n plus 1 vertices. Then it actually gives that the dimension of this VH0 is n plus 1. But there is something that we have to emphasize. So here we have 0 boundary condition, but if we use the same trick, I mean, not as an implementation that I showed last time, Robin boundary condition, but in the formulation, because we want to make our formulation a bit easier. So let's say that since we know solution at the boundary, so if this was our domain, we know solution at the boundary. So the test function on the boundary, we take it 0, because what is the basis of the space? Basis of the space is a linear independent basis functions that linear combination gives the whole element on the space. But since we know the solution on the boundary, we don't need to take test function on the boundary. It's just 0. So based on this, the dimension, so the dimension of this will be a bit different. So I I have to introduce a different notation here. So I can, let me see if I have it on my notes. Yeah, so I don't have it on my notes, but I want to make sure that let me just, I say we triangulate by n plus 1 vertices, but let me say that we have n little bar plus 1 interior vertices. So and so let's say that we have this triangulation like this. So these are interior vertices. So we have a triangulation of this first, the big domain, but we don't number the vertices which are on the diagonal, no, on the boundary. Then the interior vertices, let's say that we have n bar plus 1 interior vertices. So because of this, the dimension of this space VH0, of course, the dimension of the VH that we constructed yesterday is n plus 1, because we include also the boundary terms, the boundary points. But here we are just counting the interior points, and these are degrees of freedom of the space, because these are coefficients that we have to find to construct any element from that space. So next, we can write now variation of finite element formulation. So I call it GFEM, and it's simply find UH from VH0 such that, so integral gradient UH times gradient V dx in omega equals to integral F V dx in omega for all V from VH0. Okay, so we can do Gagliorchan orthogonality. So for Gagliorchan orthogonality, we have to subtract the weak formulation here. We have to subtract Gagliorchan formulation, actually, the right way is saying that, Gagliorchan formulation from the weak formulation. So in this part. So we see that the right-hand side, they are the same. If we are taking the test function from this finite dimensional subspace, then we get the following relation. So integral omega gradient of u minus UH gradient V dx is 0 for all V from VH0. So this relation, we usually call it Gagliorchan orthogonality. Yeah. So there is one thing that I have to mention. Remember, before the break, I say that L2 projection is closely related to, what was it? L2 projection is closely related to finite element formulation, right? So this is a L2 projection here. So now let's say that we denote this function f. So this function f, I just denoted, instead of function, I denoted by r of this function, r of UH. And this one is minus Laplacian of UH minus f, something like this. So I just took a construct a specific case of that. So if you just take this instead of f, of course, UH, it was piecewise linear. You take, piecewise polynomial in this case, of course. When you take linear, then the second derivative will be a bit problematic. You have to do this discrete Laplacian. But I'd say that UH is piecewise at least quadratic function. Then the second derivative, of course, it doesn't live in our finite element space, so they are discontinuous. Then what we say that we are looking for some best approximation of this R. So in this case, here it's going to be, instead of that function, I put RUH. And this is our space VH. We want to find some best approximation of this RUH space, RUH, in the finite element space. So you can just look to this projection. You are looking for some approximation of this R, so that this, capital R is orthogonal to the finite element space, right? Something like this. No, the error will be. Let me just. I want to mention here. I want to say that. It's not the right way of writing. I want to say that, let me just write first, then I will say. So we want to find UH from VH such that this residual UH is orthogonal to the finite element space. So how now it's not equal to that, but there is something else is equal to that. So, and this orthogonality is actually, it comes from the L2 projection. Of course, we know that the best approximation in the finite element space, it comes from the projection. So you have to project it, find the integral. I need a bit of space here. So we want to find the integral. We want to find the projection. So it is integral R UH V dx is equal to 0. And this actually gives us the residual is orthogonal to finite element space. So this is called orthogonality. When we say Gagliarkin orthogonality, we have a relation of the error with elements in the finite element space. But what I wanted to say, there was Gagliarkin orthogonality, it was integral gradient E times gradient V dx is 0 for all V from the finite element space. And here, if you do one integration by parts, it's going to be Laplacian of E, and this Laplacian of E will be the residual. So it is exactly will be that relation. So here there is a relation between L2 projection and Gagliarkin finite element formulation. So before, of course, I think historical note that we made, someone else came with this using spaces like the approximation spaces that we constructed is VH, but Gagliarkin comes and he said that how to choose this function space. So he said that, yeah, the easiest way of choosing this constructing this function space, we take the residual and we take the L2 projection of this residual to the finite element space. So this formulation and Gagliarkin formulation that we wrote it below, they are equivalent. So that's what I wanted to emphasize here. So we come back there, and by using this Gagliarkin orthogonality, now we can define our energy norm. So it's integral gradient W times gradient W dx. And we denote that difference as an error, u minus UH. And we can get the following estimate for the energy norm of the error. So little e error square equals to integral omega gradient u minus UH times u minus UH dx. And as a trick that we did before, we subtract and add test function here. And we have u minus UH times gradient u minus v dx. So I split the integrals, plus integral u minus UH times gradient of v minus UH dx. Of course, this dx bar. And if you use Gagliardian orthogonality, so this was true for any v from the finite element space. And of course, this v minus UH is also an element from that finite element space VH0. So because of that, this term is 0 due to Gagliardian orthogonality. So yeah, the rest is, we know how to do that. We use Cauchy-Schwarz to get this estimate, u minus UH, gradient of u minus v. And it's actually, if you use a definition of the L2 norm and the energy norm, so energy norm is L2 norm of the gradient, we get the following estimate. So it is u minus UH energy norm, u minus v energy norm. And if you compare now left-hand side and right-hand side, so you can divide it by the norm, and we get the following estimate. So this is u minus UH energy norm is less or equal to u minus v in the energy norm for all v from the finite element space. And this estimation is called the best approximation result. I think we did it for finite element in 1D. So it says that whatever you take from this finite element space, this UH that you find with finite element method is the best approximation of U in the finite element space with respect to the energy norm, so this norm. So this is called one of the a priori estimate. See, here we don't, I mean, it's before solving UH, we didn't go to the linear system. Before solving for UH, we know that this UH is the best approximation. You cannot find anything better than this UH in the finite element space. So that is really remarkable. I think this best approximation result is one of the things that projection methods have. So I remember I just, before doing this a priori estimate, I say that L2 projection is the same idea as Gagliardian finite element, because in the L2 projection, we have some unknown function. We want to find the projection of that unknown function in the finite element space. But Gagliardian method says that that unknown function is our residual. So we want to take a projection of the residual to the finite element space. So yeah, because of that, these methods are called projection method. If I just come back to what we wrote about the projection here. So to be correct, I have to fix it. So to be correct here, I will do like this. So I will do we have this Laplacian u, and this little guy would be our Laplacian u. So this is Laplacian of u. Then, of course, we want to find some approximation of this Laplacian of u. Here, I call this Laplacian of u h. So that the error, so this error would be Laplacian of u minus Laplacian of u h, which is actually f. So here I want to find it minus because I want to get a plus. F plus Laplacian of u h. And this is actually residual. Residual should come here. So the error, the residual should be orthogonal to the finite element space. So we don't know this element, it's somewhere outside. We want to find some type of approximation of that. So I just denote it with minus Laplacian of this. And this is the error that we get. So this method, of course, they are called projection method. And this is one of the important properties of the projection method, is that you cannot make any other best approximation in that finite element space, finite dimensional space. So I have to go now to the next step, and there is something that I want to say. So we are here now. We move to the linear system, and for the linear system, we say that UH is an element in that finite element space. Of course, then we can find some size so that this UH is written as a linear combination of the test functions. So UH is element VH0. So that means that there exists a sequence of size J is equal to 0 to n bar. So now I'm just counting interior points. I'm not the boundary part, I don't include it. So that UH is equal to linear combination J equal to 0 to n bar psi j's phi j's x. So we insert it to the finite element formulation. I rearrange and I get the following linear system. So J equals to 0 to n bar psi j's integral gradient of phi j times gradient of phi I in omega dx is equal to f phi I dx omega for all I is equal to 0 to n bar. So this is like the numbering that we get. Okay, so this object, we call it A, is a stiffness matrix. And of course, this unknown vector is psi. The right hand side is B. We ended up by solving this A psi equals to B. Okay, so there is something that I want to go through. We have a few minutes. So yesterday we had some kind of stiffness matrix in this form, and we showed that stiffness matrix is positive definite, right? We did some kind of algebra stuff, and we showed that it is positive definite. But I have to say that in general, for general boundary condition, it's actually positive semi-definite. So let me just emphasize it now, then we can discuss. But if you have a Dirichlet boundary condition, in this case 0, then it's strictly positive definite. So A is positive definite. So it says that you get any vector eta, non-zero eta, you multiply by A from the left and right, and this number will be bigger than 0. So yeah, let's do this computation. Then we can denote some element from the space from VH0 such that is a linear combination of j equal to 0 to n bar at the j phi j, like this. So now this at is a long vector by of the coefficient at the 1, at the 2, at the n, like this. Now we start from 0, like that. And if you write down this product, it will be equivalent to the double summation j. So I is equal to 0 to n at the I integral omega grad phi j grad phi I dx. And so of course there's this double summation here for j's, j equal to 0 to n bar, and here we have eta j. So this one is equal to, we just put the summation, we just rearrange the summation like we did last time. So we move this sum together with this coefficient in front of this phi, and we can pull out this gradient from the summation because the gradient of the sum is the sum of the gradients. And we do the same. Here we move it inside. There is eta. I will move this eta also in front of phi j's. So we get this integral omega gradient of sum j equal to 0 to n bar psi. No, here it is eta j phi j times gradient of the sum I equal to 0 to n bar eta I phi I dx. And like we did before, this object is actually our function w. So the whole object is w of x. This object is also w of x. Then we get the following integral w times w dx, which is the L2 norm of the w. L2 norm of the gradient of the w. Okay, now it comes this boundary condition. So yesterday we didn't mention it, and it was a bit, some of you even asked me by email. That's very important, and it's a very important question actually. So let's say that now we have this, and this w is like piecewise linear function, right? The w in 1D, it's going to be like this piecewise linear function. In 1D is like that. All right, so this norm is strictly begin at 0. If, yeah, I mean, the other way I have to say, so if the gradient of this object is non-zero, right? Because, I could remember that I think in the first lecture we recalled what is the norm of the definition of the norm. The norm of a function, the norm of the function, so I call it like this, I could get square, is 0 if and only if the argument inside the norm is 0, like this. So, but we want to show that it is positive, right? For positive definiteness, it should be positive. And if it is equal to 0 at some point, it's called positive semi-definite. But if you see, what was the boundary condition we had? We had boundary condition that W should be 0 on the omega. So in 1D case, here maybe it is 0 and here it is 1. W0 is, and W1 is equal to 0. So we want to say that this identity for us, this norm, is only 0 when W itself is 0. Because here, the gradient of W is 0. I should put like absolute value. The gradient is a vector, absolute value is a scalar. The gradient is 0. I mean, what I wanted to say, I want to say that it only happens when it is constant, and that constant is equal to 0. So in other words, let me just rewrite this guy in 1D. So in 1D, we want to show that this norm of U W prime is 0, right? For which W's, for which I don't see any faces, and it is quite weird that, now I can see in other pages. You see, it's quite weird that I'm trying to convince myself. It's not so fun. So I want to say that when this situation, occurs, for which functions W, we know that this W is piecewise linear function, for which these functions this occurs. But of course, you say that, of course, you can take this function to be any constant, right? So if you just take any constant, like this constant function, you can take many of them. I mean, there are infinitely many constant functions. If I take W to be that function, the derivative is 0. So that means that if we don't have any boundary condition or Neumann boundary condition that we had last time, this equality is not always, it's not necessarily that it is always strictly positive. So it says that there will be many constant functions that this equality is actually equal to 0. So conclusion 1 is when we have Neumann boundary condition, that means that any constant is 0, then this norm of grad W square is bigger and equal to 0. So there will be many cases that it is equal to 0. So therefore, in this situation, A is called positive semi-definite. But in this particular situation that we have, we cannot choose any constant function because we have a boundary condition. Our boundary condition is 0. So any constant function that is a solution should satisfy boundary condition. And therefore, there is only one function which is 0, right? So there is only one constant function which is 0. So the second conclusion that we make, when you have W equal to 0 as Dirichlet boundary condition, let's say that there is unique, so this notation, there is unique W is equal to 0, so that this norm is equal to 0. So there is only one, and but if W is not 0 for any non-zero function, so it's going to be W's in this shape, that means that A is strictly positive definite. So that's why in this case, A is positive definite. So for the case of Dirichlet boundary condition it is 0, then we get a conclusion that the norm is 0 only if and only if the argument is 0, but we know that the argument is 0 can be any constant. So any constant, the argument here, the derivative of the constant is of course is 0 slope, but we cannot choose any constant function because we have to respect boundary condition. In this case, it is equal to 0. That's why the only function that we satisfy this equality, it's 0 function. And this is actually a definition of the positive definiteness. Says that, where was it here? This is true for any non-zero eta. But we showed that equality holds equal to 0 only if and only if this eta is identically equal to 0. So that's why the definition of positive definiteness of this line says that A is actually positive definite when you have Dirichlet boundary condition. All right, so let's just go back to the aim and goal that we started today here. So we introduced interpolation and projection in 2D. We looked at basic estimates, of course, without proving. We learned how to construct projections in 2D. Then we continued with finite elements in 2D. It's the same formulation, but we have to be careful with the boundary term, because boundary, we have to take the normal derivative on the boundary. So there's some new stuff on that. And today, we could say something about a priori estimate, but a posteriori estimate is left. So I think we will continue next time how to do basic a posteriori estimate in 2D. So I stop here, and if you have any question, please go ahead and ask. So let me see, when do we have a lecture next time? Questions?
Yeah, I'm wondering about the energy norm. Like, what does it intuitively tell us about a function? If there's anything to say about that.
That was my question too, so that's great.
Nice.
What does it say about the function you said, or?
Yeah.
It doesn't say about the function itself, because the energy norm is actually defined by the derivative. So here, it says about the derivative of the function. And we call it energy norm because this norm is actually constructed from the differential equation, from the weak formulation. And this norm is not a unique norm that is applicable for every PDEs. For example, L2 norm, we can use for any function, right? And here it is different. This energy norm is actually, it's related to the variational formulation that we get. So in this particular case, in this particular case, the energy norm says something about the gradient of the solution, but it is not, and this is what we can say at this point.
Could you maybe introduce some context in, like, if you could relate it in some other area of physics, so you could like see at it from another perspective or something? Does it like appear somewhere else than in
but this is a good question. I don't have an answer for that, but I will bring it. I will find something until the next time.
Cool.
So if it is, because I don't know physics much, I think finite element approximation was first introduced in solid mechanics. So there were some bending, and there's a comment or numerical integration stability is assessed with the energy norm. Yeah, but that energy norm that I think Julian is saying, it's a stability norm that can use in finite difference, right, Julian? Yeah, so that is a bit different here because we also have a stability norm, but that our stability estimate is a bit different. So I wouldn't say that this energy norm, yeah.
No, but I mean, so at the end, they measure the same thing, right? When you use energy norm, well, or at least what we understand with the concept of energy in the context of numerical integration, we are just saying that we want the increase or the decrease in your temporal solutions at every iteration to not boil up to infinity. In other words, you don't want the change in the function to be infinite, and more or less that's what you're assessing with the energy norm. You're quantifying or adding up at every position the derivative of the function. So you're measuring how much it changes in a domain, or at least that's how I understand it.
Yeah, that is correct. But this has nothing to do with the energy in physics, right? Energy in physics, I think it is U square. This kinetic energy, I mean, if I recall it correctly, this is the kinetic energy without the gradient. But the energy estimate that Julian is saying, I think it's about the stability of this integral, because we are refining mesh, and this UH we are updating with different UHs. So the estimate that we showed, it shows that this numerical integration or exact integration, as whatever you like, it doesn't blow up. It's always preserved. The energy is preserved. But I mean, this one is kinetic energy, if you call energy in physics. So I don't have any relation with this kinetic energy, but I will try to find something until the next time. But it's a good question.
Cool. Thank you. Have a good day.
Yeah. You too. Any other questions? So I should mention that you have to fill this lab list, the Google document that I sent, that is needed for the lab next time.